This video is probably one of the most important videos I've made so far. In this video, I will be presenting a breakthrough that I recently had in the cosmology that I'm developing. The breakthrough has to do with the connection between complex numbers, the principle of incommensurability, and the Mandelbrot set, which is near and dear to my heart. In this video, I'm going to show you how the principle of incommensurability manifests in the very specific geometry of the Mandelbrot set itself. So strap on your thinking caps because this is going to be a doozy. In the cosmology I'm developing, incommensurability is defined as two principles with no common basis. Basically, if two domains have nothing in common, then they are thought to be incommensurate. For example, in a previous video, space and counterspace were defined as incommensurate principles. Space is not counterspace, and counterspace is not space. The concept of orthogonality plays a very important role in the principle of incommensurability. Like the principle itself, orthogonality comes in many forms. So what is orthogonality? Orthogonality, for example, can be seen in the Cartesian coordinate system. When two lines are perpendicular to each other, they are said to be orthogonal. That is, when two lines cross each other at 90 degrees, they are said to be orthogonal. As you can see, the x-axis and the y-axis form an angle of 90 degrees. So this is one of the most common examples of orthogonality. Orthogonality is almost always associated with 90 degrees. Although the concept of orthogonality is only one part of the principle of incommensurability, it is an important feature of the principle. Without orthogonality, there is no principle. Complex numbers also form an orthogonal basis. This is why they can be shown in Cartesian coordinates as seen here on the right. Although orthogonal generally interprets as perpendicular or 90 degrees, in reality it means in a direction that didn't exist before. In this image, the real axis is vertical and the imaginary axis is horizontal. This is contrary to convention, but this is the way I like it. This is my convention. So, if real numbers came first, then imaginary numbers can be thought of as a direction or dimension that didn't exist before. In the beginning was real, and God said, "Let there be imaginary." The real dimension must come first before you can define an orthogonal. This is commonly referred to as a normal. Orthogonality is normal. You can imagine another line going into and out of the page. That line would be normal to the complex plane. But we don't need to do that. Luckily, we only need two dimensions for the principle of incommensurability. Space and counterspace, charge and discharge, sink and source, real and imaginary. Incommensurability is two-dimensional. For the record, the reason I make real vertical and imaginary horizontal is so that the Mandelbrot set ends up in this upright orientation, which I really like. In this orientation, the left-right symmetry is more obvious, and it looks a little Buddha-like in this orientation as well. All that said, since the Mandelbrot set literally lives in the complex plane, this is what makes it special. I have always thought the Mandelbrot set could tell us something new and important about how the universe works. And guess what? It does. I have always thought that there was some sort of secret message hidden deep within this mathematical monster, and it turns out there is. Like Ellie Arroway and Carl Sagan's Contact, finding a secret message within the digits of pi, only better. I found the principle of incommensurability. The equation used to generate the Mandelbrot set is quite simple. Z equals Z squared plus C. This is how it is officially written. This reads Z new equals Z previous squared plus some constant. Here, both Z and C are complex numbers. Complex numbers are two-dimensional in that they have two values. R is the real coordinate and I is the imaginary coordinate. This forms a point on the complex plane. So, in complex number systems, numbers are really points. We call them numbers, but they are really just coordinates on a two-dimensional graph. So, what is so special about complex numbers? Well, in order to understand complex numbers, we first need to understand imaginary numbers. Imaginary numbers were originally invented to solve the problem, what is the square root of -1? In other words, what number multiplied by itself can give you -1? Of course, it is well known that there is no real number that, when multiplied by itself, can produce a negative number. Positive numbers times positive number give positive numbers. Negative number times negative numbers also gives positive numbers. Technically, there is no real solution to this problem. Or is there? Robert Distinti, whose work I've been following for quite some time now, Robert Distinti has come up with a way to solve this problem using only real numbers. In other words, technically there is a real solution to this problem. Robert Distinti's method, which is part of his Vortex Algebra, completely takes the mystery out of imaginary numbers. And I'm going to show you how it's done. And it's going to be really cool. Historically, to get around this problem, the powers that be created an imaginary entity and called it I for imaginary. And then they wrote I squared is equal to -1. Technically, this is true. However, there are actually two solutions to the square root of -1, positive I and negative I. So both I squared and -I squared are equal to -1. Although there are two solutions to the square root of -1, generally positive I is given as the identity of the imaginary numbers. Now, I have a problem with this, but I will get into that at another time. So, that's how it's done in practice. Imaginary numbers are still mysterious, but we now have a tool to deal with them mathematically. In order to solve the problem in the Distinti way, we need the concept of a matrix. Since complex numbers are two-dimensional, it makes sense to use a two-dimensional matrix. In standard algebra, scalars are usually thought of as one-dimensional real numbers. You can scale an object by multiplying by a real number. This is why they are called scalars. Multiplying by a number bigger than 1 expands the object. Multiplying by a number smaller than 1 contracts the objects. This is generally what scalars do. In Distinti's Vortrix Algebra, there are no one-dimensional scalars. All scalars are two-dimensional. This is what a scalar looks like in 2D. This is the identity matrix. In matrix math, scalars are always on the forward diagonal of the matrix. In Vortex Algebra, the scalar value 2 is written like this. And the scalar value of -1 is written like this. Now we're going to go back to the problem. And the problem is, what times itself is equal to -1. In Vortex Algebra, in Distinti's Vortrix Algebra, all scalars are two-dimensional, and so in Vortex Algebra, the problem is written as follows. What 2D matrix multiplied by itself is equal to the matrix on the right? The matrix on the right is the negative identity matrix. So what matrix multiplied by itself is equal to the negative identity matrix? Using matrix math, this problem is quite easy to solve. First of all, we know that there must be two solutions to a square function. Here's the first solution, and here's the second solution. These two solutions solve the problem perfectly. Using matrix math, the problem becomes so simple. Notice that all the entries within the matrix area are real values. No imaginary values are required. Now here's the cool part. These two matrices are functionally identical to the imaginary numbers. They perform the exact same function. In order to prove that this is true, I decided to apply Robert Distinti's solution to, guess what? The Mandelbrot set. Since the Mandelbrot set literally lives in the complex plane, then I should be able to write a program that uses Vortex Algebra to generate the Mandelbrot set instead of the standard way that I've been using up to now. And I did. And it does. As far as I know, this has never been done before. I have been studying the Mandelbrot set since 1985, and I have never run across this solution. This is very exciting for me. So thank you, Robert Distinti, for Vortex Algebra and your logical take on imaginary numbers. And thank you, Ken Wheeler, for the principle of incommensurability. Putting these two ideas together allows me to bring the Mandelbrot set into the picture. This allows me to use the Mandelbrot set as a teaching tool for the principle of incommensurability, which is cool. So here's how I use Vortex Algebra and the principle of incommensurability to solve the Mandelbrot set. This, for sure, has never been done before, because only a few people even know about Vortex Algebra, and the principle of incommensurability is virtually unheard of. So this is all new. This is uncharted territory. So using the Distinti notation, we write the real and imaginary scalars as follows. Here is the real scalar, and here is the two-dimensional imaginary scalar. Next, we multiply each scalar by identity. We multiply the A scalar by the real identity matrix, and this is trivial as it gives us back the same matrix. Next, we multiply the B scalar matrix by the imaginary identity matrix. This replaces I in the standard notation. This is not trivial as it produces a different matrix. This is what makes complex numbers really cool. Here I want to point out that these two matrices are incommensurate in principle. The A matrix and the B matrix have nothing in common. This is how complex numbers enter the realm of incommensurability. These two matrices are incommensurate in principle. Next, we add the two matrices from the previous slide together to generate the matrix here on the right. This matrix is now holding both the real and the imaginary components. The two incommensurate matrices are now co-joined in the same matrix. Ken Wheeler talks about the conjugate nature of the incommensurate fields. Here we can see the conjugate relationship of the so-called complex numbers. This is a complex number in matrix form. It is so much easier to understand this way. The complex number is now encoded into this matrix. These two incommensurate principles are going to work together to generate an image of the Mandelbrot set. And now we iterate. First, we set up the original matrix, and then we set Z and C, the constant, to that. Then we square it, and then we add back in the original matrix. This is the first iteration. For the second iteration and subsequent iterations, you take the output of the matrix and feed it back in as Z on the other side. And this continues for each iteration. Notice that the original matrix C is also fed back in each time. In this manner, for each iteration, the feedback loop gets something different, and it gets something the same. Different and same are incommensurate principles. Different is not same, and same is not different. In the beginning there was same, and God said, "Let there be different." So the principle of incommensurability is showing its face over and over and over again in the making of the Mandelbrot set. And that's it. That's how you render the Mandelbrot set using Vortex Algebra. Does it work? Of course it works. Here are two Mandelbrot images. The one on the left was generated the old way that I used to use. The one on the right was generated using Vortex Algebra. There are literally no differences. In case you don't believe me, I put the code I used to generate these two pictures into this description of this video. Anyone could take this code and test it for themselves. I think the most interesting thing about this whole process is the connection I see between complex numbers and the principle of incommensurability. The Mandelbrot set is an emanation of the principle of incommensurability. It is, in my humble opinion, the most important picture in the history of pictures. This is what gives me hope that I will be able to understand the universe someday, in my own time and on my own terms. Instead of unifying forces, we should be unifying principles. In the future, all of the universe will be explainable from the perspective of the principle of incommensurability. In the future, all phenomenon will be blamed on the principle of incommensurability. And in the future, the Mandelbrot set will be used as a teaching tool in the teaching of the principle of incommensurability. For example, when asked the questions, why do black holes exist, and why do black holes behave the way they do, we would invoke the principle of incommensurability. The fuzzy boundary in this image is a domain separator. It is an event horizon in the truest sense. In nature, event horizons separate incommensurate principles and are often associated with fractal geometry and self-similarity. In this case, the event horizon separates the black region from the outer gradient region, which can be loosely thought of as counterspace and space. The points in the black region of the Mandelbrot set collapse towards singularity when iterated through the function z equals z squared plus c, very much like we imagine happens inside a black hole. The points in the outer gradient region expand to infinity during the iteration process. You see, the inside points behave completely different than the outside points. I have studied them extensively and there are no similarities. The inside points and the outside points are incommensurate in principle. This is yet another way that the principle of incommensurability manifests itself inside the Mandelbrot set. At the other extreme, when asked the question, what are atoms and why do they behave the way they do, the principle of incommensurability would be invoked. The inside of the nucleus and the electron shells are incommensurate in principle. There are no similarities between these two domains. Inside the nucleus, we have quarks that experience asymptotic behavior. They cannot escape the atom, just like the black hole points inside the Mandelbrot set. Outside, we have the electron shells, and electrons can escape the atom, just like the gradient points inside the Mandelbrot set. Here we have the weak force playing the role of the domain separator. The weak force is the event horizon of the atom. The weak force is responsible for bringing things together, as in nuclear fusion events, and it is also responsible for tearing things apart, as in nuclear fission events. As you can see, the principle of incommensurability seems to apply to all scales of organized matter. Here are some other questions that we might want to ask. Why do galaxies have flat rotation curves, and why do they clump together into clusters? Why does the universe seem to be accelerating in expansion? Why is only 5% of the universe visible? This is all because of the principle of incommensurability. Notice that only a tiny portion, 5% maybe, of this image makes up the event horizon of the Mandelbrot set. This analogy can be applied to so many things. For example, it could also be applied to the cell. In the case of the cell, the outer round boundary or escape boundary is analogous to the plasma membrane. Here, the inner black region is analogous to the nucleus of the cell. The outer gradient region is analogous to the cellular material called cytoplasm. And the event horizon is analogous to, can you guess it? Yes, the event horizon is analogous to the DNA of the cell. This is where information is stored. Event horizons, in my cosmology, are information. Event horizons are information. And this is how I plan on unifying physics. Not by unifying forces, but by unifying principles and by unifying scales of organized matter. The information that I presented in this video puts the Mandelbrot set into context with some very important physics principles. The Mandelbrot set is not to be taken literally as a physical object with physical laws. The Mandelbrot set as a metaphor for the principle of incommensurability, which manifests in many, many ways in nature both physically and temporally, is the key to understanding the true nature of the universe.